Is it recording now? Okay. Is the sound working? I guess
Yes,
so.
yes,
Yeah, no, someone was asking, is the sound working? Yeah, it's the sound working. Is yeah, sound is working for me. Okay, so let's start, guys. So yeah, so I will. I mean, after every maybe two or three slides, I will just pause for some time and look at the chat questions. So don't expect like for me to respond to your chat directly, because it would be like not directly immediately, because it's difficult for me to speak and look at the chats as well. Okay, so let's start. Okay, so that's this is the lecture one of computer programming. We are the computer systems group. Yeah, so I think yeah, I'm a third year. Yeah, I'm a third year PhD student with Suresh Purni sir. That's about me. Okay, so yeah, so today in today's class, our agenda is quite simple and quite straightforward. So what we will be doing is we'll be just looking at a computing system from a programmer's point of view, as in uh, what what do you have to view your computer system as for you to program it. There's a programmer view of a computer system. Yeah. Okay, so when you think about a computing system, so two things come to mind, right? A software and a hardware. So some examples of computing systems are web browser, WhatsApp, and data center. Can you think of anything else which which defines a computer system apart from the examples that's there on the slides? Okay, so even a smart refrigerator is also a computing system. Why am I saying so? Because it has to have two main components. One would be a hardware part and one would be a software part. So hardware part is something which is which is doing the tasks for you, right? Which is doing the physical things for you, and the software is the one that's controlling the hardware. So any system which can be divided into these two, between these two like zones, is what we call a computing system to be. Even a rocket is a computing system. I mean, a rocket also has a software and a hardware. So computing system does not mean it's only a computer. It can be anything with a hardware controlled by a software above it. That's quite basic, I think. Yeah. Okay, so now let's go to hardware. So yeah, I think yeah, that's clear, right? This particular point, that what's a computing system as a whole. So it's not limited to computers only. Do you have any chat questions? No, microwave is not a computing system. You cannot program a microwave. Come on, that's a hardware. Microwave is just hardware. Yeah, smart TV. You could say today smart TVs are quite. They have a software stack above it, right? You have a whole. I mean, you could say a whole interface through which you interact with the hardware. Yeah, smartwatch is one example. Yeah, yeah. Robot is a very good example of a computing system. Robots which have this programmability aspect, right, which we can set to certain functions. Drones, yes, good, yeah. So I think you guys get this point. Let me close the chat. Yeah. Okay, so now when it comes to hardware, yeah. So in this course, right, I mean, in the very few, in the beginning lectures, at least the lectures that I will be taking, we'll be taking a very, I mean, a very ingenious approach of computer programming. I mean, we cannot start programming without without describing the thing that you are programming on, right? I mean, I mean, it's not like just like another course where you just learn a language and syntax and then start coding. It doesn't make sense, because we have to go from an engineering perspective. We have to first understand what is it that we are programming, what's the hardware like, what happens internally, and then after this two, I think 2 or 3 classes, then we will go to the software part, that is the programming part. where we will show you how to write programs for your computer. So now if you look at a typical hardware, so typical hardware, it consists of three main segments, you could say. Yeah, the first is your central processing unit, which is called the CPU. I guess all of you know in today's world what's a CPU, right? So whenever you buy a computer, all that you see is what kind of processor it has. Is it an i7? Is it a ARM? Is it something else? So that's what the CPU means. Is the central processing unit of your computer. What's main memory? Now I'm yeah guys. So now I'm explaining what are the three main components of a computer hardware. There's the CPU, the main memory, and the I/O devices. So the main memory is the memory. I mean the RAM. I mean this is the common terminology which you guys, I guess, which you guys know by now. A RAM means how much memory your computer has. I mean the higher your RAM, the better your computer performs. That's what I guess. That's what you guys know. I mean about RAM. And I/O devices are devices through which you interact with your system. Assume I give you a computer without a keyboard or mouse, or for that matter, without a display. So that doesn't make any sense, right? If you just have a CPU, you have the outside world has to interact with your system, and those interactions are enabled by the I/O devices. These are input output devices. So your keyboard is an input device, your mouse is an input device, your display, your monitor is an output device, because it is displaying something which is coming out from your computer. Is this point clear, guys? The basic three parts of any computer hardware.
Yes, sir.
Okay, cool. So before going into this slide, I would present you a very simple example. So let's say, I mean, these days, you guys are at home, right? I mean, you must be doing some household chores, for example, going to the market or doing this, doing that. Let's say your mother asks you to get something from the market nearby. So what would she give you? She would give you a list, right? She would give you a list of items, and then you take that list, you'll read the list, and then you will go to the corresponding places in the market and get those items back. So we could this task that you are doing, right, this whole thing of going to the grocers and then getting the stuff home, you can also you can divide this into three parts. So your brain is reading the list, right? So your brain is the CPU here, because it is reading, because whatever list you got, right, you are seeing that list and you are inferring like what I have to do and what not. So that's your brain is your CPU. That piece of paper where you got your items listed, that's the memory, because that is something that you have to have with you, right? Otherwise you'd forget. I mean, you don't you might miss some items. So you have to have you to have a thing where you can permanently pin down your items. So that's main memory. Your legs, your hands, those are IO devices, maybe, because that is letting you get stuff and bring it back home. Yes. So now if this example is clear, right? So now let's let's go a little bit more details into the hardware part. So so I'll be just expanding on this slide that I just described. If you see the software here, so you have a CPU, you have memory and IO devices, and the software is and the software controls, or the software interacts with these things beneath. That is, this is the previously, if you just look at this picture, right, software, then we had the hardware block. Now we have divided this hardware block into three parts: the CPU, memory, and IO devices. Now in this slide we will be looking a bit into a bit more details about the structure of the hardware. the structure of the CPU and the structure of the memory. So you, from the example, I guess you might have guessed, why do you need memory? We need memory. Uh, we need memory for storage. We need memory for remembering what to do, and for that matter, we need memory for asking the CPU to do something. So that's what the memory. That's what the memory means. So when you program a computer, right? Uh, so this is the this is the mental picture that you should have of the computer. The computer has a processing unit called the CPU, and the computer has a flat memory. By flat memory, I mean it's a continuous sequence of, let's say, a sequence of locations where you can put your uh, data. I mean, let's not define data as of now, but let's just imagine data is something. Data is something on which the CPU acts, that is the processor of your computer acts upon. So memory is that contiguous area, or that contiguous place in your hardware where you can put this data on which the CPU will act upon. That's why if you see, so memory is logically, so yeah, so there's one subtle difference here. So when I meant logically, I am giving you a logical picture of memory. In memory, you could just think of a sequence of, uh, a sequence of continuous blocks. But physically, if you just look at your DRAM chips, right, which you buy from the market. So DRAM chip, that's a memory there. That's the memory. That's the RAM memory, right, which your CPU reads from. So that memory might not look contiguous. That memory might have some different arrangement. So that's the physical view of the memory, which you as a programmer does not have to be worried about. That's how the hardware is implemented for memory. That is the physical memory uh, uh, can be different from our logical view. Our logical view is simply memory is a contiguous sequence of objects, or continuous sequence of things wherein we can put our data, or blocks rather, contiguous sequence of blocks where you can put our data for the CPU to read from. But physically, the memory chip that comes with your computer, that memory chip might be different. It might look different. It might not be contiguous. But we don't have to worry about the physical look or the physical setting from a programming perspective. From the programming perspective, all you need to know it's a contiguous sequence of. Now, how many of you guys know what was the difference between a bytes and a bit? You know what's a byte, right? Byte and a bit. Yes, just respond on the chats. Someone has I think someone has unmuted their microphone. Can you mute it back? I can hear key presses. Fine, I'll mute you. Okay, so sorry. Yes, so for people who does not know what's a byte, so just think, yeah. So memory is a contiguous sequence of blocks, right? So what is the size of a block now? The size of a block is what we call a byte. Now, yeah, now what is a byte? A byte is a sequence of 8 bits. So what's a bit? A bit is simply a 0 or a 1, right? Bit is just, what's a bit? Bit is a one bit information, as in, is it a 0 or is it a 1? So memory, you could think of a contiguous sequence of blocks. Each block is called a byte, and each byte is made up of 8 bits. By bits, I mean it's a sequence of zeros and ones. So everything that happens in your computer, I mean, from a hardware perspective, it looks like a sequence of bits, zeros and ones. Whatever programs you would be writing, right? Eventually, when it goes to your CPU, eventually when it is executed by your CPU, it sees your program as a continuous sequence of zeros and ones. That is a contiguous sequence of bytes. Yes. So is that, I think that's clear. So byte is 8 bits, and one bit is either a zero or one. So if you look at this picture here, so I spoke about memory being a contiguous space of bytes, right? So each byte here, if you just look at the right here, look on the right hand side here, you see some numbers. So each byte that's located in memory has an address. What do I mean by an address? Address is the location of that byte in your memory. Your memory is a contiguous sequence of bytes, right? So let's say I ask you, get me the 100th byte. So 100 is the address of that byte now. So without the address, you cannot access that byte. You have to know the address to go to that location in memory and fetch that byte. So that's why your memory would have, so all your memory bytes, right? The memory, this one, yeah. What all the bytes in your memory have contiguous addresses assigned. So whenever you want to fetch a particular byte, you go to that address and get that byte. So this particular thing, this particular task of going to an address and getting a byte, so that particular function is done by something called a memory controller. Is this, yeah? So why? So what happens? So whenever, see, your CPU executes, your CPU executes uh, sorry, not execute, your CPU acts upon the data, right? That is there on the memory. And what is memory? Memory is a sequence of bytes. So whenever your CPU has to act on something, it has to go to a byte. It has to go fetch that byte first, then look inside, like what is there, what is the instruction that I have to do, or what is the, just think about that list example. You read the list, right? You see, okay, I have to get this item now. So it's similar to that. Your CPU has to now think of your list, your paper as the memory. Your paper would have many lines, right? Line 1, line 2, line 3, line 4. Now the CPU, now you would go to a line number and pick up that item, and then, yeah, and you would go to a line number, you look at what the item is, and then you go and get that item. So this is exactly what the CPU does. Instead of that list, instead of that paper, you would have a memory. The CPU would now go to a specific address. The CPU would just say, okay, I go to the address 100. Okay, I get this byte, and now what is inside that byte? Okay, I have to do this now. Now it will start executing whatever is there inside that byte. So this particular task about of going to a address and getting that byte back to the CPU, because the CPU does not interact directly with the memory. The CPU says to the memory controller, give me the byte that is located at this particular XYZ address. And the memory controller would go to that address, fetch that byte, and deliver it back to the CPU. Now this delivery, right? Now this delivery happens, I mean, there has to be some kind of interconnect, right, between the CPU and the memory for them to transfer, for the CPU to transfer the address, and for the memory controller to transfer the byte at that address back to the CPU. So this exchange is done over some kind of network, right? So that's what the system bus is there for. The system bus handles these interactions, takes things from one part of your hardware, delivers it to the other, and then again takes data from that other part and delivers it to the some other part. So that's why system bus is important, to exchange the data between the different components. Any questions here? You guys can feel free to speak up on the mic.
Sir,
Yeah.
so system bus includes the wirings and all. Is it so?
Yes, I mean in a very coarse physical way, you could think of the system bus as a wiring kind of thing, but then actually it's not wiring. I mean it's again it's some logic actually. When you design computer systems, right? That is some that wiring is a very coarse word to use. So system bus, you could think of, yeah, for as of now you could think of at certain wires coming out from the CPU and going to the memory controller, but it's more than wires. It has much more logic than simple wires, because wires does not have any logic, right? Once you put something on a wire, it goes from one end to other end. But system bus is more than a wire. It has more logic attached to it. Did I make
Okay,
myself
sir.
clear?
Yes, sir.
Yeah, but yeah, in a course way, because this is not an architecture class, right? So it's fine. I mean, you could think of it as wires going from one component of the hardware to another component. Okay, anything else, guys? Any
And
questions
sir,
on this?
sir,
Yeah.
what is this physical representation of 0 and 1? So like they are literal numbers, or does this have any physical significance?
Yes. See, I can make a computer out of stones. That's
Hmm.
that's a fact. So I'll tell you. So zero and one has a physical meaning, right? I mean, zero stands for off and one stands for on. You could
So like,
actually you could make a computer out of anything until and unless you have a logic which says what is zero and what is one. Let's say I have two stones.
hmm,
I paint one stone black and one stone white. So black stone stands for zero and one stands for white. So now that's my bit there, zero and one.
so like our computer switches on and off
Yeah.
continuously.
In our computer, what happens is we look at voltages inside our circuits. So
Hmm.
when the voltage is above a certain threshold, that accounts for one. And when a voltage drops like below a certain threshold, that's a zero. So
Okay.
whatever, yeah, let me not go into the full details, but to put it quite simply, so yours, so so these zero and ones, these bits are stored in memory,
Hmm.
right? So how do you store it in memory? So in if you think in a very physical sense, so your memory, I am talking about the hard disk. So your memory will be magnetized. So hard disk is a magnetic memory, right? Hard disk, your
Yes.
physical spinning hard disk.
Hmm.
So then let's just look at a single byte in your hard disk. So in your single byte, it will have, let's say, in a single byte it will have 10 small things which are magnetized. So if they are magnetized in this direction, it means a zero. If they are magnetized in the other, let's say one points to the north and one points to the south, so the north stands for zero and the south stands for one.
Okay.
So this is the so different places. So in your hard disk, it's this magnetization which says what's a zero and what's a one. North may be zero and south may be one. In your inside your CPU, a low and a high voltage means a zero and a one.
Okay.
So zero and ones have different physical interpretations. They based on where you are. I could design a computer by just having lights like table lamps. One stands for a table lamp being off and zero, sorry, table lamp being up, zero for the table lamp being off. Yeah.
Okay. And one more doubt.
Yes.
Um, you talked about this address of bytes.
Yes.
So like the address itself is the memory of that particular byte, or is it just the location?
Think about a bookshelf, or think about a shelf, right? You guys are just out of school, so you guys must have a lot of shelves in your classroom. So what happens in a shelf? So shelf, you keep copies, right? You keep books,
Hmm.
right? So that shelf is a physical entity, that book is a physical entity, isn't it?
Yes.
Right? So but that shelf number, when I say go to that shelf, go to shelf number 5,
Hmm.
that 5 is, it's not a physical thing, right? I mean you just go to, you know that's the fifth shelf, so you go to that shelf, you get your copy out of there. So that whole shelf means a byte,
Okay.
and that shelf number means the address.
Hmm. Yeah.
right? So address need not be located, address need not be stored anywhere. Address is just a logical way of saying which shelf are you supposed, because if I just say get a copy from the shelf, like what shelf, you will be confused. I mean, everyone will be confused. You don't know what copy to get, right? Someone has to say which shelf number.
Yeah.
So that means that that is the address. The shelf number is the address, but that address is not like, it's not there like to see. You just know that that is shelf number 5.
Yeah.
Okay. Anything? Any more questions? Okay. Let me read the chats now. I think we have. You guys have a class immediately after this, right? Can someone reply?
No, sir, we don't have any
No,
class.
no, sir.
Okay. I mean, I can stretch to at least 10 minutes, I think. Yeah. Because I
Sir?
don't know. I
Yes.
may not.
Sure, sir. No,
Yes, sir.
we can stretch longer, sir, if you want. No
No, no,
problem.
I don't want to, because that's not how we are supposed to function. Yeah. Anyways, fine, good. So, any questions on the chat?
Sir,
Let me.
like IO devices are also being controlled by the system bus, sir.
Yes, yeah, that's a good question. I'll come to that. Wait, let me address the questions on the chats. Yeah, that's what it is, Narayan. It's like turning a bulb on and off. Yeah. What's the difference between storage and memory? Well, what do you mean by storage here? Do you mean hard disk storage versus RAM? I'll come to that later. We have a slide for that. Yeah, I think I've answered that. We don't need space to store addresses. Straight address is just it's just a logical thing. Like go there and get it. Okay, okay. Sorry. Yeah. So someone was asking about the IO devices. So what happens here? Okay. So as I have already described, so bus is something which helps you get in data and get out data, right? So when you have IO devices, so IO devices, what do you do in IO devices? You just input data and output data. So then when you type something on your keyboard, it has to either go to the CPU or it has to go to the it has to go to CPU and then it goes to memory, right? So let's say you enter your password. So what happens when you enter your password? First, your CPU validates whether is it a correct password or not. Sorry, whether is it the correct password or not. If it is the correct password, maybe the CPU will store it in memory. So that's why whenever this IO buses want to communicate with your system, they have to use the bus, because at the first place through the bus your input will go to the CPU, and the CPU will again send that particular input which we have just provided back to the memory. I mean to the memory through again the system bus. So system bus is something you could say it's like the roads, right? It's like the roads connecting different houses in a town. If one house wants to communicate with the other, you have to go through the roads. If the road does not lead there, you cannot go to that house. As simple as that. So did I answer your question? Whoever was asking
So that
this.
means IO devices are directly under CPU but not under system bus.
Yes, so think of the system bus. System bus has no, system bus has no brain as such. I mean, to put it in a very blunt way, since system bus is just like roads leading to CPU. So if you want to send something to the CPU through your keyboard, it has to go through the system bus. That's all the system bus does. So it does not mean it does not come under system bus. It's nothing like that. System bus is the thing which is connecting the CPU to the IO devices. If this road was not there, then your keyboard wouldn't have functioned. It's just like a road. You just type something, it goes over the road and goes inside the CPU. The CPU processes that information that you just provided through your keyboard, and then maybe stores it back on the memory or does something with that. Is this clear? Is this point clear?
Yes, sir.
Okay.
Yes, sir.
Okay. So yeah, so one more thing here. So one more point, which is the fourth point. So just look at this. Random access memory, RAM. I mean, you guys know what's a RAM, right? When you buy the RAM, you say my system has this RAM, that this much RAM, 4 GB, 8 GB RAM. So what does the word random access mean? So random access means that, let's say, again, go to the bookshelf example. Let's say I ask you to get me copy in shelf number 5. So do you have to go through shelf number 1 to shelf number 4 and then you go to shelf 5? You don't do that, right? You will be really dumb if you do that. You directly go to shelf 5 and get your book. It's not like you go to shelf 1, throw away the book, shelf 2, throw away the book, shelf 3, throw away the book, shelf 4, throw away the book, shelf 5, okay, I got the book, get it. It does not happen that way. Whatever shelf I ask you to get your book from, you go to that shelf and get your book. And each, assuming you are not lazy, and each shelf, I mean, getting the book from each shelf has almost the same access time, right? If I ask you to get from shelf number 1, it will require you the same amount of time compared to if I ask you to get your book from shelf number 100. There's no difference. This is what random access means. So whatever byte you want to get from memory, you could get it in the same time, irrespective of where that byte is located. So what would be a uniform access time? Uniform access time means, sorry, it's not uniform, non-uniform access time, versus, which means it's not random access. I mean, what will be the opposite of random access? It will be non-random access or non-uniform access time. So what would that mean is, assuming you have a pile of books, let's say you have your NCRT 1, NCRT 2, NCRT 2 up to NCRT 100. NCRT 1 is located on top, NCRT 100 is located on the 100, like it's a stack, it's a pile of books. If I ask you to get the last NCRT book, assuming it's a very heavy stack, so you cannot just pull that out, right? That last book. You have to first unload all the books above it, and then you can take out that book, assuming you don't have that strength to just pull out that book. So you have to reduce the weight on that book given by all the books on top by reducing all the books or like removing all the books, and then you get the last book. So this is something called non-uniform access, as in it depends on what I'm asking you to access. If that thing is somewhere far from you, it will take you more time. If that is near to you, it will take you less time. But RAM does not work that way. RAM has uniform access. Is this point clear, guys? This is an important point. So just keep this example always in mind. That's that pile of books and the shelf of books. The pile of books is non-uniform and the shelf book is this random access. Good. Yes.
In the just before you told me about the system bus, no, sir.
Yes. Yes.
I
Yeah.
have one more doubt with that.
Okay. Yes.
There
Tell
you
me.
told that system bus is just something connecting CPU, memory controller, and IO devices. So, like, if it is just connecting, how does the system bus know IO devices are only to be connected to the CPU and not to the memory controller? That means IO devices first need to go to the CPU and next to the memory. After processing it, the data needs to go to memory controller. No, sir.
Okay.
Like it can't go to the memory controller directly. Does the system bus do that?
Yes. Yeah, I will be going into details of architecture, but let me explain this to you. So assuming you are the delivery person, right? And I ask you to go get this thing delivered to someone in this locality. So I will give you a package, right? So what is the most essential thing that I have to write on top of that package? Just answer me.
Yes, sir.
Address.
Address, yeah. So it's same thing happens here also. So whenever you are typing something, you say there's an address located, like the first line of address is where does it go to? Does it go to a CPU or does it go to a memory? So based on that, the system bus will route it. It's like a router. It will route it to either CPU or memory. If it is meant for the CPU, that is, if the address says okay, go to CPU, then it will go to CPU. Here by address, I mean not this memory address. I mean just a physical. You could say not a physical. I mean you could say an ID. Let's say I say CPU is 0 and CPU stands for number ID 0 and memory for ID 1. So then whatever input you are giving right through your keyboard, it will have an ID associated with it. So based on the ID, the system bus will route that to this particular place, either the CPU or the memory.
So you mean that system bus can also process few things?
Yes, so that's why I told now in the very beginning, it's not wires, it's an intelligent set of wires. It has much more logic than that. It's a router.
Yes, sir, I understand.
Yeah, now you get it right. So it has to know where to deliver the packet. So yeah. What do you mean by three types of buses, Pratyush? Three types of buses. What's that?
Hello.
Yes, tell me.
So there are. I have heard that there are three types of buses, such as control bus, address bus, and data bus.
Okay, in that way, okay, because there is a lot of buses around here. I mean, in my world actually, because I deal with computer architecture, and we are in our lab we design processors, so we think of bus in a different perspective. So if you're coming from from there, then yeah, it has three types of buses: control, address, and yeah, control bus and address. Basically, two are the most important: control bus and address bus, and data bus. Yeah, sorry, the third is data bus. Let's say let's keep this question at pause. I will if I have time, let's say 10 minutes at the end, I will explain this to you because this is not exactly relevant. I mean, I will be digressing if I do that. But at the end, if within 5 minutes, I will explain this to you. Say address, memory, and data bus. Is that fine?
Yes,
Address,
sir.
control, and data bus.
Yes, sir. Thank you, sir.
Yeah. Why do you choose only binary digits to make a computer understand? Yes. Why do you do that? Tell me what is there any other way that you have thought of, Abhishek, to do this? Is there any other way? You can have a ternary logic, right? So
Means this was the first thought.
yes, so what would a ternary logic look like? What's a ternary logic? How would you represent a ternary logic, tell me, using two switches or two bulbs?
Yes, sir.
If the
0 and
bulb
1,
is
that
if
will
the
be there.
bulb is on, it is one. If the bulb is off, it is zero. Ternary logic would mean if the bulb is neither off nor on. Is it possible to have a bulb which is neither on nor off?
No, sir.
So that answers your question. Binary logic is the simplest. Binary is the simplest uh, way to uh, way to physically represent this thing, zero versus zero and ones. Because if you have something in bit, see this is. I mean, yeah, I will be digressing like light years ahead, but this is what quantum computing does. Quantum computing is not only zero and ones. It has a lot of other states as well. It has zero, it has ones, it has all these things in between as well. So that's why quantum computing is not binary logic. It's much it has more it's it's not ternary, it's higher than ternary as also, because uh, yeah, let me not go there. Yeah, because a quantum state, it can be in a lot of different state. Each state can represent a bit, so you are no longer restricted in that quantum world to zero and ones. You could have zero, zero prime, zero, zero double prime. So that's why quantum computers, if you are successful in doing like fully realizing a quantum computer commercially, then it will like change everything in this world. It will make computer way faster and way smaller. Yes, it's very different. So let's me not go there. Yeah, it's quite interesting. Quantum computing is quite interesting, quite difficult as well. There is a course in our in triple IT where you can learn about quantum computing. I mean, there are quantum algorithms, quantum computing. Why are they powerful? They are powerful just for the simple fact that quantum computing has more states than just zero and ones. So once you are able to represent more states, once you are able to represent a bulb that is half glowing, half not glowing, you have just expanded your possibilities, right? Because yeah, because 2-bit versus like say n bit is more, it's a more superior logic than 2-bit binary logic. That's what qubit means. Yeah, q states. Okay, guys, let's not no questions on for further on this quantum computing. Yeah, let me finish the lecture. Okay, 20 more minutes. Okay, good. Fine. So yeah, so now let's talk about the execution model. So I have explained you the hardware model of your computer, CPU, memory, and the IO devices system bus. Now let's go into your execution model. What do I mean by execution model? Execution model is how your CPU executes your program. That's what execution model means. Why is it called a model? Because this is not exactly how it happens. This is a much more abstracted view of things that happens internally. But in an actual architecture, there might be there will be differences. But since we are talking about a model, we have to have this unifying view, right? So all the CPU, all the processors in the world does this thing, this basic thing, execution. This is how your CPU executes. Yeah. So yeah. Okay, again, going back to that grocery example. So first thing that you have to do, now think yourself as a computer and your mom as your programmer, right? So how did your mom made you do something? She wrote down some things on a list. She wrote down 10 items on a list and then told you, go get these things. So now your mom is your programmer, right? And then that list that you wrote, sorry, the list that she wrote is the program, and the lines in that list are the instructions for you, right? For you, that is a CPU, and that piece of paper is the memory on which she wrote the instructions. So now what will be your execution model, or what will be the execution model of the CPU? It will simply read each instruction that is there on the memory, on that piece of paper. And then first, what you have to do, you have to first decode, like, okay, it's item X. Okay, what does item X mean? So item X means this, right? So that's the first thing is to go to a particular line in that list, or go to a particular address, get that byte, and see what is inside that byte. Like what is your mom asking you to get, or what is the programmer telling the computer to do? So that's the decode part. You have to understand, you have to know what is it. If there is an item, let's say, uh, which you don't know, which you have never seen in the before in your life, then you cannot get that, right? So you cannot decode it. So it's as simple as that. Once you fetch an instruction from your memory, you have to first decode that instruction, and then once you have decoded, now you know what you have to do. That is the third step. Third step is go execute it. Go get it from the market. So that's the third step. Fetch, read the line from the list, read the byte from the address, decode, read the item what is there on the list, right? Or read the byte that is there on the address. Third, go get the item, and from a CPU perspective, execute that instruction. Yeah, now the instructions. Now, what do I mean by instruction? Instructions could be of three types, basically three types. Computations, you do an addition, subtraction, multiplication, right? It's the most basic thing that you do. Control transfer, and read, modify, write data. Someone's mic is on here. Namrata, let me mute you. Yeah. Okay. Yes. So we are clear on the fetch part, we are clear on the decode part. Now let's come to the execute. So the execute, whenever CPU decodes an instruction, that instruction would be of either A, B, or C type. So what do A is the most basic one, right? So you have a CPU. CPU is a fancy calculator. So calculator does add, subtractions, minus, divisions. So CPU has to be able to do that. So that's the first class. That's the first type of instructions. That is basic computations. What is control transfer? Control, I'll not go into detail. We will discuss this at length in this course, but in a very brief way, control transfer means you jump between the instructions. That is, do this instruction and then go instruction 1, 2, 3, again come back, or go do this or do that. So control transfers are like if and else instructions. So let's say your mom writes this thing down. Go to market 1. If this item is there in market 1 at lesser price, get it from market 1. If this item is else, go to market 2. Right? So this is This is a control transfer. What is your mom asking you to do? Your mom is asking you to look at something and then either do this or do that. You are not doing both, right? Based on the price of the item in the market, you are either going to market 1 or market 2. So that's what we mean by control transfer instruction. It is asking you to do either do this or do that, or don't do anything at all. I mean, if this is not available, don't get it. So those kind of instructions are not computations, right? You are not adding, multiplying, or you are not getting something from the market. You are deciding whether to go here or there. That's control transfer. So what's read, modify data? Read, modify, write. Yeah. So read, modify, write is again memory. It has to do with memory. So okay, it's fine that you got your items from the list and then you went to market 1 or market 2. Now you would strike something off from the list, right? I mean, let's say you got a toothpaste, strike. You got pencil and pen, strike. So this is, you are modifying the list because you have done this task. You are changing the list now. That is, you are now, the list is memory here. So you are modifying the things in memory. So this is where the third kind of instructions come into play. These are called read, modify, write instructions. That is, you are going to memory and changing something in memory based on the actions that you have performed before. Okay, so once your instruction falls into either of these 3 categories, then you go back to step 1 and repeat the same thing with the next instruction. That's all. So this is your execution model 101, guys. This is it. Simple fetch, decode, execute. Execute would be of 3 types: either add, either computations, control, or read, modify, write, and then go back and do the same things again for the next instruction. You keep on doing this until you run out of instructions. That's it, until you reach the end of your list. This is important, guys. So any questions here?
So, is there any kind of key to decode these instructions?
Yes, that's what your CPU, I mean, what would your CPU do otherwise? Your CPU has all these keys inside it. The CPU will match the key to the instruction that you fetched. If the key matches, and then that means it is this type of instruction.
So, like, we write in alphabets and they convert it into binary digits via key.
What do you mean by key here?
Like, keys to decode something, like a particular alphabet is being signified by a zeros and ones.
Yes. Yeah.
Okay.
Yeah. So that's, so here the key means, so whatever instructions you will be getting from memory, those instructions will be decoded, right? They'll be broken down into zeros and ones, because all your computer sees, all your CPU sees is zeros and ones. Now for that particular instruction, it would have a pattern, right? If let's say if your pattern is 0101, that means instruction 1. If your pattern is 0, if your pattern is 1111, that means it's instruction 2. Or it is instruction type 2. So this is what the decoder does. It has its in memory. It already has this pre-stored pre-stored keys, right? Let's say 000 stands for this type of addresses, this type of instructions. So whenever you get an instruction broken down into bits, you match that instructions against your table, that is your keys. So whatever it matches to, you execute that instruction. It will match to either a computation, control, or read, modify, write type of instruction, and accordingly you go and execute that.
Okay.
See, key simply you could say what to yeah, you could say key is like a mask. I mean, again, you guys would be confused on mask here. So what do I mean is, it's just like a template. I mean, you guys might have drawn some tattoo over your hand, right? So when you put the tattoo and then you put the paint and the tattoo comes out on your hand. So it's something like that. You take your instruction and put it on a template. So if the template matches exactly, right? If there's a one-on-one matching, that means that's the template. I mean, that's the instruction that you have to execute. That's the type of instruction that you have to execute. So key is something like that. It's something that matches. So you have a list of keys, and then you match your instruction to one of the keys, and whatever is true, whichever match is true, you execute that type of instruction based on yeah, I mean it will be either a compute, control, or read, modify, write. Yeah, so think of this as, yeah, key is an algorithm or a template. What's a branch call? Wait, let me see how many slides do I have. Yes. Okay. Okay. Okay, so I explained you what's a branch call, right? So assume on your list, Hardik, yeah. So just after this explanation, just let me know if I have explained it to you or not. So what's a branch call? So what happens is, so when you are reading the items of your list, so all of a sudden you see an instructions written by your mom saying, if item X, okay, yeah. So your mom writes this. If item X is at lower prices in market 1, go to market 1. Otherwise, go to market 2. So that means when you read this instruction, what do you see? You see that your mom has written this particular thing, as in either you have to do this or that, right? So this particular instruction, how do you classify it? It's not a computation instruction, right? You are not performing any compute, neither are you writing some things on the list or in memory. You are either doing this or doing that based on a condition. What is the condition? If that item is uh, 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 present at a lower price in this market, go to that, otherwise go to this. So these kind of instructions are called a branch instructions. You have one point, and based on that condition, you either branch to this part or you branch to that part of your execution. Did I make myself clear, Hardik? Okay, good. Okay. Yeah, so decoder is not a program. So decoder is something that is inside your CPU, right? So anything that is inside your CPU is not program, it's hardware. It's a bunch of and and or gates. So anything inside your CPU is not program. Program is something that will be there on the memory. Program is a set of instructions. Okay, good. Okay, so this is the basic execution model. The instructions will be on memory. The CPU will go to the memory address, fetch an instruction, see what is the instruction all about. Based on that decoded information, it will either do a compute, control, or read, modify, write, and then repeat the same thing all over again for the next instruction. It's as simple as that. And then the CPU will do this tirelessly for all the instructions in your program. Good. Okay, yeah, so I forgot this point. So yeah, so when you read your program from memory, your program would have two parts to it, right? One part would be, what is the program all about? What are the instructions in the program? Do this, do that, do this, do that. Like, these are the instructions. They also have to be loaded in memory, right? Otherwise, how would the CPU know what to do? The other part of your program will be data. Now, what is this data? Data is something which would be, yeah. Now you can read it here. So data would be something. I am explaining this part, guys, this data part. Instructions are, I have explained already what the CPU will be doing. Data is, your program would be generating something, right? Your program will it will not be very simple program, right? It will do some computations, it will create some data. That is what is the data part of your program. That is, once it creates this data, it has to store it back, right, to memory. That's one thing. That is, your program will operate, it will perform instructions through the CPU, and whenever your program is generating some data, it has to be stored back on the memory. So that's the data part. That's the first part. That is, your program is generating data internally. The other part would be what? let's say uh, yeah, so let's say you write a program, to find out the topper in your class, right? So what do you have to do? You first have to write the instructions to do that. How do you find out the topper? You take the data of each you take the data of each student, add all the values, that is all the marks, all the subjects of all the marks, sorry, all the marks of all the subjects, and then whoever is the highest, that's the topper. So this is your logic, right? These are the instructions that you have to write. Take the data, sorry, take all the marks from each student, add the marks up, and then compare all the marks of all the students and report whoever is the highest. So that's your instruction. Now what is the data part here? You have to provide your program with marks of each student, right? Without that, your program just simply cannot function. So that is the data part of your program. Your program cannot be always, or just keep this thing in mind, that your program cannot only be instructions, because instructions has to act upon data. If there is no data, your instructions are meaningless, right? What will it act upon? So data is that part of your program which your instructions consume and provide you an output finally. As you can see here, the data can be,
It's 11 o'clock.
yeah, as you can see here, data can be, as I've already explained, it can be generated within the program. It can, for example, yeah, for example, you take, yeah, so what in this student example, what is the data that you have generated internally? The data that you have generated from your program is the name of the topper. That's the data that was not given to your program, right? That is something that you have generated. So that data, the name of the topper, is the generated part of the program or the execution. What was the data that was given to it from externally from the memory? That was the student marks. That was data provided externally. And the first part, and the first kind of data would be, let's say, something that you directly write inside your program. As in, you say, if your let's say now within the students you have to fail some students. So if the student marks falls below this, then the student is failed. So that particular number, right, let's say 50 or 60, that has not come from anywhere. That is, you have written that as a part of the instruction. So that is the data which is part of the instruction itself. It is not being fed from anywhere, or it is not created inside the program. It is linked with an instruction. It is part of an instruction. Any questions here, guys? Yeah, so right now I am only, when I'm talking about instructions now, I'm talking about assembly instructions only, that the machine understands. So later on, when you write C programs, that means you will be writing instructions in a higher level language, and those program instructions would be again translated to assembly instructions for your CPU to understand. CPU does not understand your C programs. CPU does not understand your Java programs as they are. You write a Java program, you say read this Java program and give me the, your CPU can't simply do this. There are a lot of things that happen between you writing your program and the CPU executing your program. There's a lot of softwares that are there in between these two steps. What does all those softwares do is, they will take your program and convert it to something that the CPU understands. And what does the CPU understand? The CPU understands machine code or assembly code. So the CPU will always execute assembly code, but then it is the responsibility of other softwares, for example, a compiler, a loader, a linker, for for them to take your high level program written in Java or Python or C and then convert it to an assembly for the CPU to execute through that execution model which I just explained. Decode is not about compiling. Compiling is something which I just explained. taking your high level program, converting it to assembly. That's compiling. Decoding is uh, decoding is when you see an assembly instruction, what kind of assembly is it? Is it a control instruction? Is it an add instruction? Is it a read modify write instruction? So that is the decoding part. That is the decoding is in the hardware. It's inside the CPU. It's a chip. Your CPU is made up of multiple chips, like small logic. Decoder or decoding is one of the logics that is there on the CPU. Okay, anything else, guys? Any other questions? So when we write a program, other program variables store permanently in memory or store temporarily. They are stored temporarily during execution. Excuse me, sir. They are stored temporarily during execution. They are not stored permanently because they are part of your program, right? So when your program is done executing, the variables are gone. See, it's as simple as that now. So let's say I am talking to you, right? So we are doing this, right? We are doing this lecture here. So now things are going to memory, right? And then I am speaking. So when you switch off your computer and you log in back to Zoom, do you see this again? You don't see this, right? It has just vanished. So that's what the program will also do. While they are executing, they will store data in the memory, read data, do data. But then when the program is done executing, all those data are erased from memory. That's why it's volatile memory. RAM is volatile memory. Once the program finishes, all the data is erased from memory. Or for that matter, you play games, right? So whenever you switch off your computer, that the game memory is gone until and unless you decided to permanently store in the hard disk. There's a save button in game, right? Saving point. So when you do the save button, a snapshot of your game is stored on your hard disk, and hard disk is permanent storage. It goes there permanently. But if you don't do that saving, then whatever things you are playing, right, they were all in the RAM. That's volatile memory. If you shut down your computer, all that memory is gone, all the data is gone. Okay, after compiling the system, go to decoder. I just cannot get away with decoder. Is it? Decoder is coming back again and again. Wait. Narayan, I'll explain it to you. Wait, let me see what else. Yes, did I answer your question?
Yes, sir.
Yeah, okay. So let me see but why dynamic local memory doesn't get deleted after execution and is code to delete it. No, it's not like you terminate from task manager. If you close the game, that's it. That's it. Game is like a program now. So if you close the game, your whatever memory that game was generating, it was writing in the RAM, reading from it. All the data is gone because the program is gone. You don't have to terminate from task manager. If you close it, it's gone. Second type of data. Okay, second type of data. Wait, let me see if I have missed any questions. Second type of data. Okay. Okay, provide externally to the program. Okay. So what would be a second kind of data? I'm thinking of an example here. Wait. Okay, yeah. So it's as simple as that. Now, so uh, let's say, yeah. So let's say you log into a website, right? You log into a website. So what is the first thing that you do in a website? You type in your password. So that data that you just entered, so your program, think of your website as your program which is running. So now when you type in your password, that is the data that you are providing to the program externally. So once your website receives that password, what will it do? What is the first instruction? Let's say a high level instruction that it will execute. It will match the password, right? So the instruction here is matching the password, and the data here which you have sent from your keyboard externally is your password. Did I answer your question? Shreyans, just type in yes or no.
So, like the input is an example of externally provided data.
Exactly.
Okay.
Otherwise, you see the
Yes,
name itself
that answers my
signifies, right?
question.
It's an externally provided data. So input is something which is coming out from externally to the program.
Thank you, sir. That
Yeah.
answers my question
Okay.
perfectly.
Good. If a process is present in task manager, does it consume physical memory? Yes, it does. It does. Physical, by physical memory you mean RAM. Yeah, it consumes physical memory. So there will be some process, for example, this operating system that we are running, right? Your Windows and all these things. These are some things which are already, you don't have to execute an operating system, right? It just boots up. I'll come to that in the last slide. So there are some programs which will always be running on the background. Yeah, so these programs consume physical memory. That is, they consume RAM. But when you switch off your computer, whatever data was there, even from these programs, though that data is also lost. Anything that is there on the RAM is lost when you switch off your computer. Anything that is there on your hard disk stays forever.
Sir,
Just remember this. Yeah.
so in the shutdown, there is a code written such that the RAM will be erased. Is there something like that? If we
I have to again go to architecture. Yeah. Why? You don't have to erase the RAM. See how the RAM behaves is right. It's something like it's something I told you about those magnetic things, right? Did you get that point? What I was trying to explain, that magnetic orientations, right? If it is
No,
north.
sir, actually I didn't. I was about to ask that next.
Okay, see, you represent zeros and ones, right? On the RAM, you put zeros and ones. That's all. If you just look inside the RAM, it's a sequence of zeros and ones. I mean, it's a sequence of bytes, and again, bytes is a sequence of 8 bits, right? Each byte is a sequence of 8 bits. So that
Yes,
means,
sir.
yeah, so that means if you just open up a RAM, if you just look, if you are small enough so that you can see inside the RAM, you all that you'll see is 0 1 0 1 0 1 0 1. But this 0 and 1 0 and 1, they don't stay 0 and 1 always. Just remember this, because your RAM hardware is something like uh, let's say yeah, I mean it's a very bad example, but let's think of, you have some nails like represent your let's say you have picked up a byte from your, RAM, and that byte has 8 nails inside it, nails, right? So if the nail is pointing north, that is 0. If the nail is pointing south, it is 1, let's say, right? Now that nail will not always stay in that position. It never stays. Let's say you somehow make the nail point to north, right? So within a byte you make the first nail point north and the other nail point south, the second nail, that is second bit. But then after, let's say, for some microseconds, they go bad. I mean, their directions are not in that same way again. So what you have to do in RAM is you have to keep on refreshing the RAM. So what do I mean by refreshing? You have to send a set of you have to send a set of impulses so that the nails stay in the same position as they were supposed to. That is the north and south positions. So that's why there is something called a refreshing operations in RAM. So whenever your computer is on, your RAM is always refreshed so that your nails stay in the positions that they are supposed to. The moment you switch off your computer, that refreshing operation is gone, because there is no impulse, there is no current now to do the refreshing. And that's why your RAM, whatever data you had, right, all the nails will lose orientation and then your data is gone. So that's why you don't have to physically erase things from memory, from the RAM. Once you switch off your computer, that impulse which will refresh, which will keep the nails in position, is automatically gone, which means your data is automatically vanished. Did I make myself clear? I went very deep into architecture actually. It's that, I mean, I explained you DRAM refresh rate in the first day of your class. I don't know, I should have done this or not. But this is something called a DRAM. I mean, when you go to computer architecture, you will see this. It's called a DRAM refresh rate. So you have to refresh all the bytes in your DRAM every, let's say, every millisecond or every microsecond, so that the nails stay in position, because once they lose position, right, one north, west, east, west happens, north, east, whatever, then your zeros and ones are flipped, and then you have lost your data. So it's very important. Okay, good. That's why it's called dynamic RAM. That's why DDR, because that's not one. It's not like once you place a nail in certain position, it stays in that always. You have to dynamically refresh it always for the nail to stay in that position. I don't know how many. I think I have lost most of you for this example, but yeah, let's carry on. Okay, doesn't RAM good. Let's not go into resistor or capacitor. Even I don't know. Yeah, okay, fine. Let's now go into this. Yeah. So I think I have explained this to you already. So what's a program? So this slide says a program is a sequence of bits. That's all. So why does it say so? Because just read the steps one by one. A program is a sequence of instructions and data, right? And every instruction or every data is just a byte that is located in your RAM. If you just go to this picture here, so every instruction and every data is just byte. They are just one of the books in your shelf, just a byte, right? And every byte is a sequence of 8 bits. So what can you say from that? If A is to B is to C, then A is to C, right? Just like this logic that you have done, I think, in class 12. So that's what it means. Program is a sequence of bits. Why? Because program is a sequence of instruction is a sequence of bytes, byte is a sequence of bits, sorry, 8 bits. That's why program is a sequence of bits. I think this slide is quite clear. Okay, I think we are done with one more. Let me see how much by how much. Okay. So now I have 2 more slides. Yes. Okay. So in this slide, what did I explain to you? I explained to you how the CPU executes your program that is located in memory by reading data again from your memory, which might have come from externally or which might have been fed inside the program itself. But your program is not always in the memory, right? For example, when you want to play a game, if you switch on your computer, does your game starts automatically? It does not, right?
Okay.
It never starts automatically. What do you have to do? You have to go to the location of the game in your hard disk. That is, you go to the folder, you double click on the game.exe, and whenever you do that, that double click will do a lot of things actually under the hood. So the first thing that will do is that exe is nothing but all the instructions, all your machine instructions, or the CPU instructions that comprises your program. So whenever you double click on the exe, all these instructions will be loaded onto RAM. That is your logical memory, sequence of bytes. Now, that's the first part. It will be loaded onto the memory. Then there will be someone, a master, which would say, okay, I have loaded the exe into memory. Now start executing the instructions which were inside this exe. So this is where the transfer happens, the transfer of control. So the transfer is controlled, so the control is transferred to the CPU, and the CPU will start executing the instructions one after another. Is this point clear, guys? Your program, whenever you switch on your computer, your program does not start automatically. You have to load your program first. In most of your cases, I mean, yeah, when you do programming, then you would know how this loading happens. But in the most simplest of the scenarios, you double click a icon, double click an exe, and that double click will do the loading part for you. And then after that, whichever thing loaded, right, that thing will transfer the control to the CPU now and ask the CPU to start reading the instructions. What's the first thing that particular whichever thing gave the control to the CPU? What's the first thing that it has to do? It has to say that your instructions are located at this address in memory. Now start reading from that address, because your memory is a very big area. I mean, it's a very big sequence of bytes, right? So it has to say ki your program starts from byte, let's say byte 200. Now the CPU will go to byte 200, read the first instruction, decode it, execute it, then go to byte, the next byte, again do the same thing, and keep on doing this until it sees an end of instructions, as in there will be a separate instruction which says okay, now end here. Any questions on this slide, guys? You can type in. Is this clear? Okay, good. I think I got one yes. Device controller hub. Okay, good. So what's this device controller hub here? I'll come to that, which string transfers. I'll come to the next slide. Wait. We will post the recording, I mean, on the website. There's a course website. Once the class is done, it will take some time to process the recording, then we'll post it after this. Okay, guys. So what's the device controller? The device controller is nothing. It's just like, there's a hard disk here, right? So what is a hard disk? The hard disk is a very different piece of hardware. That is the hard. If you open up your motherboard, or if you open up your CPU, this is your motherboard, right? So do you see the hard disk on the motherboard? Do you see this? I think you guys must have at least seen a motherboard by now. So in a motherboard, the hard disk is not inside the motherboard. The hard disk is somewhere outside the motherboard, right? So that means it's not, yeah. So this is the CPU here. So these are the RAMs here. So this is your memory here. This is the CPU here. So hard disk is something which is not located on the motherboard. So it is located somewhere outside, right? So that's why you need a device controller which will interact with the hard disk. Now this device controller hub will be, it's just like a wire, you could say, which will wire this hard disk to your motherboard. So this device controller will bring in data from your hard disk, feed it to the RAM in your motherboard, and this RAM will feed it to the CPU, something like that, in a very, very coarse way. So this is the RAM, this is the main memory, this is your hard disk. This main memory will go here in the yellow strips here. This square here is the CPU. So the device controller is one of these hubs here on the motherboard, and which interacts with the hard disk, gets the data, brings it in memory, and then feeds the CPU. That's it. Fine. So this is our last slide. So what happens? So who loads the program? Yeah. So this is clear, right? I think this is clear. So again, hard disk will load your executable and then into memory. Then memory will have your instructions and data. And then, yeah, and this part remains the same as we have explained already before. CPU, system bus, and memory controller. Now we have added the hard disk to the picture just because of this reason, as in your program, to bring your program into memory. That's what the hard disk, to store your program permanently, so that when you double click its executable file, it can be loaded onto memory. That's what the hard disk is for, to storing your programs permanently. Yes. So someone is asking me who does the transfer of control? So this thing that I told you, right? So when you double click the exe, it will be loaded onto memory. So there is a program. There's a program which does this. That program is called loader. The loader is the program which will, whenever you double click an executable file, that file gets loaded onto memory. That task of loading is done by the loader. Now, I think an obvious question would have come to your mind, as in who does the loading of the OS, right? So whenever you press the power button on your computer, the OS just boots up. You never double click an OS icon, right? Or you never double click an OS executable. It automatically boots up. So who is doing that? So there is something called, there's something called a BIOS. BIOS is that blue screen which you see. I mean, it used to be there in the desktops, right? I mean, I don't know, it's not, maybe not there in the laptops, but in a desktop, when you press F8, when it program starts, then you see a BIOS screen. That's a blue screen. So BIOS stands for basic input output. So what does the BIOS do? BIOS knows that in what location of your hard disk is the executable of your operating system loaded. It will go to that location, take that executable and load it onto memory. Now there is a word called firmware. What is a firmware? Firmware is, see, there's a software which is soft. Soft is something which you can change. You can it's like you can mold it into different shapes, right? That's called software. Firmware is something which is firm. I mean, firmware is a software which you cannot change. That's what a firmware is. So BIOS is a firmware. So BIOS is like this permanent set of instructions. Permanent set. I mean, you cannot change those instructions. That's why it's called firmware. BIOS is this permanent sequence of instructions which is there in something called a read-only memory. Read-only, ROM, ROM. So that memory is never erased. That's read-only. Whatever you do to your computer, that memory will always be there. So BIOS is a sequence of instructions called firmware, which is it's like hardwired into this ROM, so that whenever you switch on your computer, these instructions are the first instructions to get executed. That is the BIOS. And these instructions will go to a location in your hard disk where your OS is located and then load it into memory. After that, everything starts. I mean, after that, I mean, your life is rosy. So you could just say, now your OS has booted up. Now the other stuffs will be there. Now you can write your programs. Now you could do your other stuff. But the first step is always done by the BIOS of loading the OS. So this is the part here. If you see the OS here, right? This is the OS part. So this is something called the kernel. Kernel is the most basic part of the OS. You don't need everything in the OS upfront. To load an OS, to load Windows, you don't need entire Windows to be loaded. You just need the Windows kernel. Once the kernel is loaded in memory and the CPU starts executing the instructions inside this part, your OS is up. The rest of the things, for example, whenever you switch on your computer, your display comes up, right? The Windows, the status bar, your clock, everything. So those things are not loaded by BIOS. Those things will be loaded by the kernel itself. But the kernel, which is the core of the operating system, that would be loaded by the BIOS in some area of your RAM. And the other things in your OS, which is the non-essential things, those will be loaded by the kernel itself. After that, your operating system is fully up and running. Now you can start writing your programs. You can start double clicking your executables on your hard disk and start doing that execution cycle, which I've explained before. Okay, so that brings us to the end of today's lecture. So this is what it is. Computing system, two things: hardware, CPU, memory, IO devices. I've explained that, I guess, enough. Software is what? Again, software is application software. What Zoom is an application software, right? The thing that we are communicating with is an application software. It's not an essential software. What's a system software? System software is an essential software. Your OS kernel is an essential software. Without this, you cannot operate on your computer. Now, in between these two extremes, that is essential and non-essential, as in application software and essential operating system kernel, there are a set of softwares called system softwares. Your compiler, that loader that I explained, which loads your executable to your memory, those are system softwares. System softwares are something which is part, which you have not written yourself, which is part of your operating system, and which comes into play when you are trying to execute certain application softwares. So application softwares use these system softwares to execute themselves. Without the system softwares, you cannot execute any application software. So that's the software part of it. OS kernel, system softwares, and then finally your application, your game, your Zoom, your browser. And finally, at the very end, you have to make all these things possible. You have your CPU, memory, and I/O devices. Without these three, without this basic hardware, you cannot do any of these things above. That is, you cannot run any of the softwares. So that's what a computing system looks like. Okay, so that brings us to the end of today's lecture. If you just see, these are the things which we have spoken about today: CPU, then main memory, then the hard disk, and this is your motherboard. If you open up your desktop, you would see something like this. Yeah, that's the summary components of a computing system execution model. Okay, so there would be, yeah, so I think we'll be putting it on the site. So regarding BIOS, right? So there will be two short videos, I think 10-15 minutes long. So you can see what's BIOS is in more details in these two videos. So yeah, we will be putting these two videos also as well on the website, the course website. You can just follow those videos there. I think these questions also, what's the process? Yeah, so you could, you guys can just note these questions down, maybe answer it in the next class. So just ask yourself what these questions and then try to answer them by looking in your computer. What's your processor? What's the size of your memory? And what's the size of your hard disk? Just these three questions. I mean, I think you guys know this already, but anyways, just keep a note of these questions. So this is like you know your basic three things, right? So CPU, the main memory, and the RAM with which you interact. Like, okay, so that's it, guys. Any questions now? I think I have. It's already half an hour. Yeah, 1.5 hours. Yeah. There is no tutorial today, and I don't. Yeah, there's no tutorial. We will see whenever. Yeah, so we have to add all of you guys to the course website. So when you get the course website, you will have access to this video recordings as well as the slides. So yeah, so wait for a couple of days because you guys have just started, right? So and then you could see your things coming up on the website. If BIOS is stored on the read-only memory, how are we able to update it? Yeah, so so that part is not BIOS. Whatever you see on the blue screen, right? That is not BIOS. That is a configurable part. Maybe you could say configurable part of the BIOS. It's a very limited set of configurations, right? It's not, you cannot change everything there. You could just say load from, what is the boot order? The boot order would be CD, CD-ROM, then hard disk, or this and that. So there are a very limited set of configuration options in that blue screen. That is not part of the BIOS. That is like an interface of BIOS, but that is not the BIOS itself. That read-only part is not that. You are not changing the read-only part through that in screen. You are changing some basic settings actually. I think attendance would be recorded based on this recording itself. I mean, I can see the list of participants here. I mean, at the very beginning of the lecture, we will see the participants and list it accordingly. Attendance, sorry. Question slides. Okay, let me put it. Yeah, I'll put it on the questions, and then if you guys have any questions, just feel free to speak up on the mic now. I will not be speaking now. Yeah, the YouTube link will be put on the course website as well, so you can follow the link from there. Can you upload the slide in the chat? Yeah, so the slides will also be there in the course website. I mean, I'll not be giving it to you directly in the chat. That will be there in the course website. The course website will contain the recording of today's lecture, the slide that I have presented, as well as the YouTube links. Can you have can you links in the chat, sir? If you are that impatient, let me see. We could have waited. Wait, let me copy paste it. Yeah. Sorry, I have done it privately. I should have done it to everyone. Yes, any questions on the lecture today, guys? Because the course, yeah, all this logistics issue will be I mean, people are dealing with this right now, because this is your second day of classes now, so it takes some, because and there are 100 of you, so 98 of you, sorry, so it will take some time to get it up, but don't worry, things will fall in place. Any questions on today's lecture? This is fine, all these things will be taken care of.